calculating the sample size. So imagine that you're going out, you want to take a sample, and you know ahead of time how much error you want to have. You know how big you want your confidence interval to be. And you know what level of confidence you want, let's say 95%, for example. Well, there is a way, just like when we knew the sample size, we could calculate the interval. You can work backwards from the interval to calculate the confidence level. And first, I'm just going to give you a quick overview of where this came from. If you don't completely follow it, it will be okay if you just trust in the formula at the end, but I would like to show it to you and give you a chance to try to understand where this is coming from. So we have our z-score to x value equation, where we take x bar and we add z times sigma. And that's going to give us our x value if we ever need to calculate one. Well, whenever we're working with a situation where we have a sample, this standard deviation right here, this sigma, is actually referring to the one that we've written as sigma x bar, or the sampling distribution standard deviation, the one that gets calculated from the central limit theorem. And we usually think of that as whatever our original standard deviation is, divided by the square root of our sample size, so divided by the square root of n. So basically what we're doing is we're taking this chunk here, we're throwing it in right there. For the z, we're using the special value of z, the z-score, that corresponds to the middle 95% if we're using a 95% confidence interval. So in that case, the z-score would be negative 1.96 on the low end and positive 1.96 on the high end. So the same number, but one's positive, one's negative. And then our x bar is just our sample mean. So if you take this and you assume that it's referring to this part up here, and you take your sigma and you assume it's this, you could rewrite this equation here to look something a little more like this. X equals, just like before, x bar. Instead of just plus, we're going to say plus or minus because we have the negative z and the positive z, and they're the same number, just one's positive, one's a negative, so we'll say plus or minus. And instead of putting z, we're going to call it z star. Z star is just a way of saying a value like this that is a special value for a confidence interval, called a critical value. And then here we have the part that we drew above. We have our original standard deviation divided by the square root of n. So this formula right here is just another way of rewriting what we've already been doing. It's the way that if you pulled out a traditional statistics textbook, it would look something like this in the writing. But how does that help us figure out the sample size? Well, if we know the standard error ahead of time, we know how big the interval will be. So we want to know the standard error. The standard error is the part that's being added or subtracted from the mean. This part right here. So that's the part we're going to focus on. We already know our mean is what it is, our sample mean, plus or minus the standard error. So we're going to focus on the standard error. And so I rewrote this part here, z star times sigma over the square root of n is equal to our standard error. Well, if we want to solve it for sample size, let's just do a little bit of algebra and move some stuff around. Divide both sides by standard error, multiply both sides by the square root of n, and you're going to be looking at something like this. So all I did is took this equation, did some algebra, and got down to here. Draw a little arrow just so we can see this progress. And then finally, if I'm solving for n and I have the square root of n, I need to square both sides. So I'll square the right side to get n, and then I'll square the left side, and I'll just have all of that in the in parentheses, all squared. So this is the equation to figure out what our sample size will be. We'll take our critical value z, so something like a 1.96. We'll have our original standard deviation, not the new one, because we can't even calculate the new one if we don't know n. So we're going to use our original standard deviation here, and we're going to divide by the amount of error that we find tolerable. The width of, I guess it would be technically half of the width of the confidence interval, because it's plus this amount from the mean and minus this amount from the mean. So this here is the big money formula, the one that you're going to want to write down. And then we're going to use this in a couple examples real quick. So let's take a look at this example here. We have a sample mean of 2178 and a sigma of 120. Now, the sample mean here of 2178 is actually extraneous information for this. It doesn't matter what the mean is as far as calculating sample size. The only thing that matters is our standard deviation, our sigma here. So our sigma of 120 is the only thing we're actually going to use out of these. The other thing that we need to look at is what kind of interval are we using. We're going to say we have a 95% confidence interval, and the maximum amount of error that we're going to tolerate is 30. So the maximum above or below the mean that we'll allow is 30 units, whatever units we're working in here. So let's go ahead and set up our equation. The first part, z star, is the critical value of z. This is the z-score that corresponds to the 95% confidence. And if you remember, that's going to be 1.96. Hopefully you've written that down somewhere. That'll come up quite a few times. So the z-score for 95% confidence interval is 1.96. So we'll write that in our formula here. We have 1.96 times our standard deviation. That's referring to just the entire population, so that's sigma x here, times 120. And that's going to be over our standard error, our maximum standard error, which is 30, we said. That's the maximum amount of error in either direction that we'll tolerate. Square that whole thing, and that's going to give us our sample size. So let's take out our calculator here. We're going to have 1.96 times 120 divided by 30, and that's going to leave us with 7.84. We're going to square that number. We have to square that whole part, leaving us with a sample size of 61.4656. Except, does that make any sense? Remember, sample size, for example, would refer to the number of people that you would go out and ask. You're going to go out and ask 61.46 people? I don't think so. So whenever you're dealing with sample size, you're going to round up. Always up. Even if it's 61.1, you're going to round it up to 62. You might say, why would you do that? Well, imagine that it was 61. Imagine that you decided to round down the way that you normally round. If you rounded down and you went back to your calculator and you did a z interval and you figured it out was 61, the error would be just a little bit over 30. But 30 is the maximum. 30 is the maximum error. So you're going to need that one extra person in order to make sure that you go below 30 for your error, because this is the max. So your error can be 29.5 or something like that, and that's totally fine. But 30.2, whatever it might come out to, would be unacceptable given these parameters. So whenever you're doing sample size calculations, always, always, always round up, even if it's 24. Let's do one more example. All right. So we have a sample mean of 83 in this new distribution, a standard deviation of 9. We're looking for a 99% confidence level, and our maximum standard error is only 2. So my guess is we're going to need a pretty big sample in order to accommodate all of this. But let's take a look and find out. Our z star is the critical value of z that refers to the interval. So 99% confidence interval for z. The z-score that corresponds to that is going to be 2.576. That's something either you already have written down or you would calculate using inverse normal on your calculator. So 2.576 is our critical value of z. We'll write that in now. 2.576. And that's going to be multiplied by our standard deviation here, sigma. Again, that's referring to the population. So times 9 over our maximum standard error. So that's all going to be over our maximum standard error of 2. And that whole side is going to get squared. So let's take out our calculator and see what we're going to get for n. 2.576 times 9 divided by 2. Square that whole side. And 134 point something. And we always, always, always round up. So we're going to get a sample size of 135. Now, you might notice that I made this promise that we're never going to use the interval, and yet here I am using z star instead of something to do with t. The reason I do that is that z is pretty straightforward to calculate, t is not. So whenever we're doing sample size predictions, usually the only time that you would calculate your sample size is if it's going to be reasonably large anyways. You wouldn't calculate your sample size to find out that you only need 12 people. Very often, at least. I mean, I guess you could. But whenever you're dealing with anything 30 and above, this equation is going to be close enough that that it will be okay to use. So whenever you're dealing with an n greater than 30, it shouldn't be an issue. So even though this equation is not perfectly matched to the t-distribution that we're using for most of our confidence intervals now, it'll be okay. So just remember to have those three main values written down for the 90% confidence, the 95% confidence, and the 99% confidence. And those z-star values will come up a lot whenever you need to use this equation. And that's all for calculating sample size for a specific confidence interval.